Okay, so we will talk about elliptic curve over a prime ZP. So, elliptic curve points over ZP. So far we have seen the elliptic curve over R. So, this is defined as E is the set x y. So, these are coming from R cross R. Sorry. So, this is the elliptic curve over R such that y square equal to x cube plus ax plus b, where a b are also real constant, satisfy that non-singularity condition. 4a cube plus 27b square is not equal to 0. Along with this point at infinity, this is the elliptic curve over R. Elliptic curve, this set is elliptic curve points over R. Okay. So, now we talk about elliptic curve points over ZP. So, instead of R, so we want to discuss this over ZP. Elliptic curve points, elliptic curve over ZP, where P is a prime. P is a prime number. So, this we want to discuss now. Okay, so elliptic curve over ZP, similar to this, we can define like this. It is the set of all points, pair of points x y, such that they are coming from ZP, both x and y, and y square is congruent to x cube plus ax plus b. So, mod p. So, every operation is under mod p, and this a b, where a b are coming from ZP, such that this non-singularity condition will satisfy, such that 4 a cube plus 27 b square is not congruent to 0 mod p. So, this set along with the point at infinity. Okay. So, this set and all the points are coming from ZP. Earlier it was coming from R. So, now our set is from ZP, and these points are satisfying this this modulo equation, like y square equal to x cube plus ax plus b mod p, and this a b are coming from ZP again, and we have a non-singularity condition. This is the elliptic curve, non-singular elliptic curve over ZP, non-singular elliptic curve over ZP. Okay. So, now if we having this is congruent to 0 mod p, then the corresponding elliptic curve is a singular elliptic curve over ZP, but we will talk about non-singular elliptic curve over ZP, and we will see that it will form a groove under the addition. Like we have seen that this E along with the plus will form a group and under the addition. So, we have to define the addition operation over here on the ZP. So, let us recall the addition operation over R. So, if we are considering this elliptic curve over R, then if we take 2 point p q, p is equal to say x 1 y 1 and q is equal to x 2 y 2. Okay, and if q is equal to minus p, we know that p plus of minus p, it is the point at infinity, and if p not equal to, or if q not equal to minus p, then we know that p plus q is equal to r, which is basically x 3 y 3, and we have the formula for x 3 y 3 like this. So, x 3 is basically lambda square minus x 1 minus x 2, and y3 is basically lambda into x1 minus x3 minus y1, and lambda is the slope, is either it is a chord or the tangent in the curve. So, depending on whether this p equal to q or p not equal to q. If p not equal to q, then this will be a chord like. So, this was the picture for R. So, this was the picture for R. So, this is the x axis, y axis, and this is the curve. Okay, so this is 2 points P Q. So, this is P, this is Q, and this is the third point of intersection, and this is our. So, if this is R prime, this is our R, the mirror image on of this point with respect to x axis, and this is our x3, y3. This is in over R cross R, elliptic curve point over R. So, this is basically if P not equal to Q, if they are different point, then this is a chord, and then the slope of this is basically y2 minus y1 by x2 minus x1 if P not equal to Q, and if P is equal to Q, then they are basically same point, and this will be basically a, if P is equal to Q, they are same point, and this will be a tangent on that point, and in that case we need to take the derivative of this equation, y square equal to x cube plus ax plus b. So, 2y dy dx equal to 3x square plus a. So, dy dx at the point x1 y1 is basically 3x1 square plus a by 2y1. So, this is basically 3x1 square plus a by 2y1 if P is equal to Q. Okay, if P is equal to Q. So, this is the formula for P plus Q. Now, we want to have the same kind of thing for over this ZP. Now, our points are coming from ZP. So, if you take 2 points from this set of curve, now our points are coming from ZP. So, if you take 2 points PQ x1 y1, which is basically from E, and Q is also x2 y2, which is basically from E. Now, this x1 y1, x2 y2 are basically coming from ZP. Okay. So, then we define this addition. If P is equal to minus Q or Q is equal to minus P, then we know P plus, this is the point at infinity. Now, if P is not equal to minus Q or Q is not equal to minus P, then we define the addition as P plus Q is equal to R, which is x3 y3, which is a point in ZP cross ZP, and which is defined similar to this. So, x3 is equal to lambda square minus x1 minus x2. So, these all operations are under mod P. So, this is mod P, and then y3 is equal to lambda into x1 minus x3 minus y1 mod P, and now the lambda is basically so the lambda is the slope, but the here points are from ZP. So, lambda will be equal to y2 minus y1, then x2 minus x1 inverse mod p. Mod p if p not equal to q, and it is 3 x1 square plus a into 2 y0 inverse mod p, small p, if p is equal to q. So, this is the formula. This is the formula we have to use to find the addition points of PQ. Okay. So, this is the addition, how we define the addition over 2 points, 2 elliptic curve points over ZP. And now the question is this. So, this will also form a groove. We have seen that E along with this addition is a abelian groove. Abelian groove with identity element that point at infinity. Okay. Now, the question is how we can find the points of the elliptic curve over ZP. So, that is the next step we will do. So, how to find the points on the elliptic curve? What are the points? So, suppose we have this elliptic curve y square equal to x cube plus a x plus b mod p. So, these x y's are coming from ZP. So, x is coming from ZP, y is coming from ZP. So, what we do? So, we form a table of x. So, x is ZP means what are the values x can take? So, x can take value 0, 1, 2, 3 up to p minus 1. Okay. So, 0, 1, 2, 3 up to p minus 1, and then corresponding to x we compute this x cube plus a x plus b mod p. We compute this value by putting these values of x, and we have values z1, z2, like these are corresponding y's. So, y1, y2 like this, these are corresponding y's. Okay. Now, the question is, now we have to check whether this is a quadratic residue or not. So, if you recall the quadratic residue, we have to check whether this is a quadratic residue mod p or not. So, that checking we will come to the what is the quadratic residue. We have seen that, we will again recap that the quadratic. So, we check whether this quantity is quadratic residue or not. That means, we say x is a quadratic residue. So, this is the definition. X belongs to ZP is a quadratic residue modulo p if and only if y square is congruent to x mod p has a solution y in ZP. So, this is the definition of quadratic residue. We say a point x from ZP is a quadratic residue if and only if it has a square root sort of. So, if and only if there exists a y such that y square equal to x has a solution in ZP. Now, suppose we take p is equal to 11. For example, if we take p is equal to 11, then we have to check what the quadratic residue under this. So, if you take p is equal to 11, so now if you just calculate this, so plus minus 1 square is 1. We consider all the points before 11. So, plus minus 5 square is basically 3, plus minus 4 square. So, these are all under plus minus, sorry. So, we can check that this coordinate, this 3 4 1 3 4 5 and 9, these are the quadratic residue mod p, because for this we have a square root. So, basically that plus minus 1 square is 1, plus minus 2 square is 4, plus minus 3 square is basically 9. So, 9 is basically again 1. So, 9 is plus minus 3 square. So, sorry, it is 9. So, this is Z 11 actually. So, plus minus 4 square. So, it is basically 16. So, 16 means 5 and plus minus 5 square like this is basically 25, then it is basically 3 like this. So, basically so if you continue like this, we will get only these numbers 1 3 4 5 9. So, these are the quadratic residue under mod 11. So, these are the points which is having the square root. Now, the question is how we can check a number is a quadratic residue or not. So, that we know, we can check this from Euler criteria. So, what is that Euler criteria? This is to check whether a point y is a quadratic residue or not. So, the problem is so this to check the quadratic residue, the problem is we have given a integer x from ZP and we need to check whether is Z y is a quadratic residue mod p or not. Okay. So, this is we can check using what is called Euler criteria. So, this is telling, this is a theorem, x is a quadratic residue, quadratic residue mod p if and only if, this is the necessary and sufficient condition, if and only if this x to the power p minus 1 by 2, x to the power p minus 1 whole divided by 2 is congruent to 1 mod p or not. Okay. This proof of this theorem we have seen. So, this is not too tough to prove, because this is the one way we have seen this, because if we assume x is a quadratic residue, that means x, there exists a y such that y square equal to x. So, that means we can just put it here. So, y x to the power p minus 1 by 2 is basically y square, and y is belongs to z p, and p is a prime. So, y square. So, this is basically p minus 1. So, this is basically congruent to 1 mod p by the Fermat's theorem. This we have seen. Now, the reverse also true. If we take this as a if this is true, then we can show that it has a square root. So, this proof we have seen. Okay. So, now this way we can check whether this is a quadratic residue or not. So, that means, so this is our y. So, we have to check that so we calculate this y. Now, we have to check whether y is a quadratic residue or not. So, to check this, we will use the Euler criteria. We will just check y to the power p minus 1 by 2 whether this is congruent to 1 mod p or not. If this is 1 mod p, then it is a quadratic residue, otherwise not. Okay. So, suppose it is a quadratic residue, then how to get the square root? So, here is a theorem. It is telling, suppose z is a quadratic residue, mod p, and p is congruent to 3 mod 4, suppose in particular case, this is a particular case, then the two square root, of z mod p are basically plus minus z to the power p plus 1 by 4 mod p. Okay. So, this is the way we get the square root, provided p is in this form. Okay. Now, let us take an example, and we will see how we can find the points over elliptic curve points over z p. So, let us take that p is equal to 11, and let us take a curve over z 11 and calculate the points on that curve. Okay. So, this is an example. So, here we are taking p is equal to 11, and we are taking this curve y square equal to, so we need to choose a b from z 11. We are taking this curve y square equal to x cube plus a x, a is 1, plus 6 over z 11. Okay. Okay. Now, what we do? We compute, so x is coming from z 11. So, we compute all the values of, for all the values of x. So, x is taking value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, these are the values x can take. Now, we have to compute this x cube plus x plus 6 mod 11. So, if we put 0 over here, it is basically 6. It is better to draw a separate line for this. Okay. So, now, if you put a 1 over here, so this is 1 plus 1, 2 plus 6, it is basically 8. If you put 2 over here, 2 cube 8 plus 2, 10 plus 1 16, 16 mod 11, this is basically 5. So, similar way if we calculate, we are getting this 3, then for 8, then 4, then for 6 we are getting 8, then for 7 we are getting 4. So, just put the value and take the mod 11. For 8 we are getting 9, and then for 9, for 8 we are getting 9, for 9 we are getting 7, and for 10 we are getting 4. So, these are my y's. Now, we need to check whether this is a quadratic residue or not. So, to check that, we need to check this is a quadratic residue or not. So, we need to apply the Euler criteria. So, that means we need to check that whether that y to the power p minus 1 by 2 is congruent to 1 mod p or not. So, here p is equal to 11. So, y to the power 5 is congruent to 1 mod p or not. So, we just take this value to the power 5 and we take mod and we check whether this is 1 or not. So, if we check that, then we can say this is no, and this is no, this is yes, this is yes, no, yes, no, yes, yes, no, yes. Now, this is the quadratic residue or not. We checked using this Euler criteria. Now, we need to find out this square root. So, this is no, this is no. So, this is a quadratic residue. So, we need to find out the square root. So, square root formula, if here p is equal to p is 11, which is basically 3 mod 14, 3 mod 4. So, that means square root will be z to the power p plus 1 by 4 mod p. So, if you do so, then we are getting these points as 4 minus 4, and that is basically 7, then 5 minus 5 6. So, this is 2 comma 9, and this will be again 2 comma 9, and this will be 3 comma 8, and this will be 2 comma 9. So, this is the square root corresponding to this plus minus z. So, for minus, so minus 4 is basically 7, minus 5 is 6, like this. So, we got the points. So, points are basically, so this is x, and we have two options for y. So, these are the point 2 comma 4, 2 comma 7, then 3 comma 5, then these are the points on the elliptic curve. So, let us just write the points. So, just quickly let us write the points. So, the points are basically 2 comma 7, then 2 comma 4, sorry 2 comma 7 and 2 comma 4, and 2 comma 4, and then we have 3 comma 5, 3 comma 6, and we have 5 comma 2, then 5 comma 9, and then we have 7 comma 2 and 7 comma 9, and we have 8 comma 3, 8 comma 8, and finally we have 10 comma 2 and 10 comma 9. So, these are my elliptic curve points along with this. This is the elliptic curve, that elliptic curve x cube plus, so y square equal to congruent to x cube plus x plus 6 mod 11. So, that means, so these are the points. So, there are total 13 points. So, 12 and sorry, yeah. So, there are total 13 points, 12 plus 1, 13 points on this curve. So, this is the elliptic curve points over ZP over Z11. Now, the question is how we can have the how we can form the groove using the points, and how we can have a crypto system based on this point. So, this we will discuss in the next class. Thank you.